All right, happy Friday. It's time to get started on Chapter 27, Fluid, Electrolyte, and Acid-Base Balance. Okay, so here are our objectives. Again, we need to understand how water is balanced in the body to maintain homeostasis. And then in many cases, how water flows is based upon our electrolyte content and our solute concentration. So we're going to actually see the changes to electrolyte, and the solutes are going to influence very greatly our water levels. And then we'll finally hit on acid base. And that's probably the part I really want you to focus on, is the acid base part, because it's going to tie back to urinary so closely. Okay? All right, so fluid balance. This is about water. This is about osmosis. Okay, we have two big compartments of water. We have water in our body that's actually inside cells, inside membranes, separated from the outside environment, and that's known as our intracellular fluid. And then we have the fluid outside of the cells, in our plasma, in the space between cells, and that's our extracellular fluid, and that's also subdivided into interstitial and plasma. Okay. And we have 70% of our body is water. And that water is between what's inside the cell versus what's outside the cell. And water is going to move into the cells or out of the cells and out from the outside of the cells, from the interstitial into the plasma, from the plasma into the interstitial fluid, based upon pressure and based upon the concentration of solutes. Okay, so we have to regulate fluid balance by regulating pressure and by regulating fluid balance through ion concentrations. Okay? So when we look at, again, fluid balance, how much water we gain in a given day has to be about equal to how much water is lost in a given day. And where do we get water? We get water from metabolism. So go back and look at that equation of glucose breaking down with oxygen. Glucose and oxygen break down completely to carbon dioxide and water. So through some of our chemical reactions, we gain water molecules. We don't gain a lot this way, but we gain some. The rest of our water coming into our body has to come from the digestive tract, as the water found in cells of food, particles found inside food, and then water that comes in as part of drinking soda, tea, coffee, as well as water pure. Water loss occurs in our body, whether we want it to or not. It's going to occur with the fecal matter because, it's important that it's somewhat liquid, so it's easier to pass out of the anal passageways. We're going to lose water in the skin. Think about the stratified squamous epithelium of our skin, the cornea layer, stratum corneum. Those cells are dead. And as they died, one of the things that they gave up was their intracellular water. And so the water initially left the inside of the cell to the extracellular space. And there's not a lot of space in the skin, but that little bit of space led to some loss of water with conduction and evaporative cooling, and that's our insensible perspiration. When we sweat for temperature regulation, that's known as sensible perspiration. And we do that with sweat glands putting water specifically on the exterior of our skin. But insensible perspiration is the water lost from as the cells are dying. That water is released into the extracellular area. And sometimes if those cells are pretty close to the surface of the skin, that water can evaporate, can be lost to the outside environment incidentally, and so it's insensible perspiration. Now remember, breathing, one of the things we do with breathing is as the air comes in, we humidify it. And so we lose, every minute we take anywhere from 12 to 16 breaths. So every minute we're losing a little bit of water to humidifying the air. And we do that to make sure that we then, once water, air, environment at the alveoli, it's easier for things to pass into the system. The last place we lose water is the urinary system. And this is the primary route for water loss and the best place to then regulate our water loss to try to compensate for maybe insufficient intake. Okay. All right. When we look at the electrolyte balance, in many cases, the ions, the solute concentration of the plasma, the solute concentration of our interstitial fluid, and the solute concentration of the intracellular fluid is going to come back to some of these key electrolytes. Electrolytes are solutes. It's just these are solutes, these are ions in many cases, that are going to play a role in generating electrical impulses, action potentials on neurons, action potentials, electrical impulses on muscle cells. So it's the neurons or the ions that have the ability to play a role in graded potentials and action potentials. And so it's still part of the solutes. So while phosphates, while glucose, amino acids, fibrinogen are going to be dissolved plasma solutes, dissolved interstitial solutes. They are not considered electrolytes because they don't play a role in conducting electrical signals at the neuron and at the muscle level, or maintaining resting membrane potentials of cells. So of the solutes that we spend a little bit more extra attention on are going to be the ones related to electrical impulses, and that's sodium, that's potassium, that's calcium, and that's chloride. Okay, so those are the big four that we're going to spend attention to. Now again, most of our solutes are going to be somewhat concentrated either inside the cell or outside the cell. And based upon those concentration gradients, that's going to lead to some dynamics in many cases of whether or not molecules or solutes want to move into or out of the cell, and could change some of the cell dynamics related to, in our electrolyte case, electrical potentials. So again, our major electrolyte, sodium, is typically found high outside the cell, low inside the cell. And if you go back to the neuron, that was driving a chemical and electrical gradient where sodium wanted to come electrically and chemically into the cell. And we manipulated that to make rapid depolarization for action potentials and for slow depolarization from resting membrane potential to threshold. Right? Potassium is the opposite. Potassium is hoarded inside the cell to counteract some of all the electrical negative proteins and phosphates and things and amino acids. And potassium is high inside the cell and low outside the cell. So chemically, potassium wants to go from high concentration inside the cell to outside the cell, but electrically, potassium wants to stay as a positively charged ion in the cell. And so that dynamic allows the cell to hoard a lot of potassium and somewhat set resting membrane potential at around negative 90 millivolts. Okay. Calcium normally is sequestered in the cells. There's usually not a lot of calcium free-floating in the cells. I mean, look at our muscle cells. They sequester it in the SCR. But there is some calcium in the cell cytoplasm because it can be recruited to be a second messenger or a cofactor. And conversely, it's very low levels, usually outside the cell. Magnesium is somewhat like calcium. It's more inside the cell than outside. And chloride is it's one of our anions, a negatively charged ion. Now, chemically, chloride is higher concentration outside the cell and low concentrations in the cell. So chemically, it wants to move from the outside of the cell into the cell because that's where the high to low is going on. Electrically, though, chloride is a negatively charged ion. So chloride actually doesn't want to electrically move into the cell because that would just put it around more negatively charged things. So electrically, chloride actually wants to stay outside of the cell versus moving into the cell. Okay, so we see that chloride is accumulating outside of the cell versus inside. And we see phosphate, bicarbonate, and phosphates are usually higher, especially phosphates, because phosphates form the phosphate backbone of DNA, of RNA. They can be parts of buffering systems for hydrogen ions. So they tend to be hoarded inside the cell, and they are some of those, again, negatively charged things that we accumulate in the cell and need potassium as a positively charged ion to offset. And bicarb can be, again, manipulated based upon calcium levels, but we see because of the carbonic anhydrase generating some that we tend to hold it in the plasma as a circulating buffer. Okay. All right, so acid-base balance. Again, it's going to return a little bit to what is the level of hydrogen ions and what is the level of some of our important buffers such as bicarb. Okay. As hydrogen ions accumulate, that means the concentration of hydrogen ions increases, so by the logarithmic scale, our pH levels decrease. Okay, and if our decreased pH levels get below 7.35 in the extracellular fluid, specifically in the plasma, that becomes an acidotic condition. And acidosis can occur because of respiratory mechanisms or metabolic mechanisms, meaning our acid load could increase because our concentration of carbon dioxide levels are increasing because the respiratory system is not getting carbon dioxide out at the lungs, and that would be a respiratory acidosis. Or hydrogen ions can increase because carbon dioxide is increasing from the cells. And so cellular levels are increasing carbon dioxide, and so therefore we have a metabolic reason. Another reason hydrogen ions could increase is because lactic acid is increasing, and therefore another metabolic means. A third would be something like you don't have enough glucose, you are then making keto acids to maintain energy output, ATP, and so you're generating more acid to keep cells working with ATP. Okay, so those are metabolic means. And again, we typically are acid-making factories. So our goal between respiratory, breathing out carbon dioxide, adequately ventilating our cells to get rid of a sufficient amount of carbon dioxide, and then adequately having the urinary system remove and secrete acid into the urine are our ways to keep acid-base balance. Now, there are some conditions and some mechanisms and some reasons where we could have an issue of too much base or too little base, but normally the focus is on getting rid of the acids that we are constantly producing. And we'll go through that a little bit more later on. Okay, and it keeps going too fast. All right, so let's focus on water. Again, water is normally in two big compartments of our body. It's either inside cells or it's outside cells, right? And water moves between these two surfaces through solute concentrations, which is osmosis, a form of diffusion where water moves from an area of high or low solute concentration where it's pretty dilute to an area of high solute concentration where it would be very concentrated, low water to solute ratio, so water wants to add and try to bring the dilution down, okay, or make it more dilute. All right, and moving ions between the ICF and ECF is going to influence then the solute concentration and therefore potentially alter water pull in or pull out. And in many cases, ions move by diffusion, by passive mechanisms, or by carrier-mediated transport because ions can't move into fat areas because it's charged and hydrophobic. So proteins have to be embedded, and these proteins might be pores, might be ligand-gated or voltage-gated channels, and might have conditions where they let the ions move. Okay? Again, our extracellular solute content is lots of different things, and it varies based on where you are in the body and what's going on in that area of the body. All right, so our extracellular content is going to be very heavy in electrolytes, and we talked about it. Sodium is a big one, chloride's a big one, and some bicarbonate. There are going to be proteins, and again, depending upon where you're located, those might be amino acids, those might be antibodies, those might be hormones, those might be a bunch of different proteins, enzymes. There's going to be some glucose, some fatty acids, and there's going to be some waste products. That might be lactic acid, that might be keto acids, that might be carbon dioxide, carbonic acid, so lots of different potential urea, ammonia, creatine, lots of different items. Okay. So again, how water moves is about what is the solute concentration in the extracellular fluid versus what is it in the ICF. If the solutes are equal, so meaning what at the outside of the cell, it's isotonic, meaning the number of solutes per liter of water is equivalent to what is the solutes per liter of water inside the cell, then the water is in balance and will not move into or out of the cell and not move into or out of the interstitial fluid. Okay? But we know that because there are constantly changes occurring in our extracellular fluid, because there's constantly changes occurring at the plasma with things coming out at the kidneys, things coming out at the respiratory, things coming out at the skin, things coming out or in at the digestive tract, that we change the ECF in anytime plasma blood moves through tissues. And because that change is occurring at the the ICF responds. It responds by giving up or drawing in water from the or giving up or drawing in certain ions or other solutes depending upon what's going on in the Okay? And when we look at our solutes, and specifically our electrolytes and our ions, we usually divide them into what are the positively charged ions and versus the negatively charged ions. So, cations are positively charged, anions are negatively charged. Again, this inside of the cell tends to have a lot of negatively charged proteins, a lot of phosphate ions, which are negative. And so therefore, it tends to hoard potassium and magnesium as its two positively charged cations to compensate and maintain the cell net basically a neutral item. Right? And again, osmolarity tends to be 300 milliosmoles. Okay? And the outside of the cell, sodium is the main positive, chloride and bicarbonate are your negatives. Okay? And there's a little bit of calcium, a little bit of potassium, a little bit of those other positives, but sodium's your main cation. And again, when we're at isotonic, the outside of the cell is at about 300 milliosmoles per liter, and so we have basically no changes to water balance between the extracellular and the intracellular environment. Okay? So again, some of the big concepts of how water is going to move into or out of the cells is going to occur, and whether or not we maintain water homeostasis, it's all about maintaining and monitoring and adjusting the solutes and the extracellular environment. So we don't actually keep account on every single cell what its solutes are and where its water table is at. We do that instead at the extracellular side, and specifically in the plasma, and as the plasma flows into the urinary system, the respiratory system, the skin, and in the digestive tract. Okay? The second big key concept to note is we don't actually have a water table. We don't actually have something that's measuring water levels. We measure fluid by measuring blood pressure, by measuring stretch on the stretch receptors of the plasma as it moves through the tubing. Okay? And so we don't directly measure then water levels. We measure water pressure as blood pressure. And we don't actually measure electrolyte balance. We don't actually measure sodium levels, potassium levels, chloride levels, calcium levels. Again, we indirectly measure them by measuring blood pressure. If there are more electrolytes, there would potentially be higher solutes in our system and more fluid would be retained, and that would then lead to more pressure. Okay? Again, cells are not going to definitely measure and move water molecules by themselves. Cells then can only really transport or change water content by changing their electrolyte and their solute concentration. Right? And so the last concept about water and fluid balance is that the body's water or electro content will rise or be lost based upon balancing what's coming in from the diet, what's coming in from extraneous circumstances, IVs, drugs, fluids, and balancing that to what's lost by breathing, by having food move through the alimentary canal, by insensible and sensible perspiration, and urinary regulation and control. Okay. Now, there are some hormonal components to regulating body water, and we've talked about these in the last chapter. Water can be regulated with the brain sensing changes in osmolarity, in blood pressure, through the hypothalamus releasing at the posterior pituitary the hormone ADH. And ADH travels to the nephrons in the kidneys, putting aquaporin, so water then can be retained as filtrate passes through the distal portion of the distal convoluted tubule and the collecting duct, and utilizing, again, that osmolarity gradient of high solute concentration in the kidney's medulla versus what's in the filtrate and drawing more water in. Aldosterone is a way to manipulate water levels, and aldosterone isn't about keeping water, it's about keeping sodium. So by keeping sodium ions in the distal convoluted tubule that have been in the filtrate and keeping more of them, and then in some ways releasing some potassium ions. Water then is retained as sodium ions are retained. Okay? And then nitric peptides work at the distal convoluted tubule to block sodium reabsorption. And so by blocking sodium reabsorption, therefore, more sodium ends up, more solutes in the filtrate in the DCT in the collecting duct. And so the osmolarity gradient might not be as great, and so more water is then lost as more solutes are lost into urine. Okay? So again, just to kind of summarize it, water losses, again, your body, whether you mean to or not, is going to lose 2,500 milliliters of water a day, so 2.5 liters. It's going to lose that because it's going to breathe. It's going to lose that because you're going to have a little fecal matter of food moving through the alimentary canal. You're going to lose it because cells are dying in your skin, losing their water, and some of that water is lost in the extracellular space to the environmental mechanisms because it's close to the surface of the skin. And then you can lose even more per day if you're even sweating. And so that 2.5 liters can become 6.5 liters because you could lose up to 4 liters of water from forced sweating, from sweating that involves on purpose trying to bring body temperature down. All right? So in general, if we're not sweating and trying to maintain body temperature with water evaporative mechanisms, we need to bring in about 2,500 milliliters or 2.5 liters every day. And most of that water is gained through food and diet, eating and drinking. A little bit by metabolic, again, breaking down glucose and some other metabolic reactions, but most of it has to come in from outside mechanisms. Okay. So in summary, again, water is going to move into cells, out of cells, into the plasma, out of the plasma, into the interstitial fluid, out of the interstitial fluid by just pure osmosis, passive diffusion of where is the highest solute concentration. And we do not directly measure water levels. We do not measure solute levels. We instead regulate water balance by measuring pressure of the fluid of plasma moving through the tubes, and then enhance or decrease the water loss and the electrolyte loss at the kidneys, at the respiratory tract, and with, again, hormones released and other mechanisms at the kidney and the brain. Okay. Now, again, I told you the electrolyte balance is going to be tied to the water balance. But in addition to keeping electrolytes, because of course we want to keep fluid, the other reason to monitor electrolytes is to keep electrical gradients and cells that have electrical impulses correctly keeping their chemical and electrical gradients for these specific ions. So again, ion sodium is going to be mostly in the extracellular fluid. And you need the sodium to be really high outside the cell and really low inside the cell. So you can use sodium to rapidly depolarize membranes for electrical impulses to be passed down the neuron, or for muscle cells to then be triggered to contract, and for, you know, that acetylcholine receptor ligand-gated sodium channel. Okay? So you work very hard in cells to keep a low sodium content. You have a sodium potassium pump that helps you keep sodium outside the cell, and you expend a lot of energy to do that. And then we keep this gradient of high sodium outside, low sodium inside to help us then in the digestive tract pull in like glucose and amino acids and fuels into the cells. And then we use it at the nephron to help us reabsorb at the PCT and the loop that drive for sodium wanting to come into the cell to help then co-transport other organic molecules. When we look at sodium balance, again, when sodium levels start to get high, we don't know that. We just see high sodium is going to be high blood pressure, because if there's high sodium, there's more water being retained, and therefore blood pressure increases. And so in trying to maintain sodium balance, we then are going to sacrifice water balance with it. So if sodium is high, that should then mean, and it doesn't always, but it should mean there's high blood pressure, high water content. So all of our mechanisms to reduce blood pressure in some ways help us reduce sodium content. Okay, so aldosterone being blocked, ADH being blocked, and nitric peptides help us dump and keep more sodium in our filtrate, sodium lost in the urine. On the opposite end, if the blood pressure is decreasing, our thought process is water's down because the electrolytes and the solutes are down. So if we retain more sodium from the filtrate, retain and gain more sodium from our diet, crave more sodium in our diet, we'll do a better job of retaining and keeping water. Okay? Now, potassium is the opposite of sodium. It's high inside the cell versus out, and we work very hard to keep potassium levels low outside of the cell. And part of that goes back to that's important for resting membrane potentials for neurons. That's important for resting membrane potentials for cells in the heart and for spontaneously depolarizing pacemaker cells. So you want to keep your potassium in the cell, and you work with that sodium-potassium pump for any potassium that gets out of a cell through leaky mechanisms and through spontaneously combusting cells, exploding, pulling it into the cells around it. And so you spend a lot of energy keeping potassium inside the cells, right? And you gain potassium through digestive processes like, eating bananas, and then you lose it and you actually secrete it when aldosterone is present in the kidneys to be higher concentrations in the urine, okay? So potassium loss in the urine is regulated, again, by regulating in some ways the sodium reabsorption. Because if you take sodium levels into the cell, and you do that a lot, that sodium in the cell needs to be pumped into the interstitial fluid, and that involves a sodium-potassium pump. And to keep 3 sodiums, you lose 2 potassiums. Okay, so in some ways, trying to bring blood pressure up, trying to retain sodium might mean a net loss of potassium and could set you up, if you're not taking in sufficient amounts of potassium in your diet, a hypokalemic event. All right. Now, old people really worry about the potassium levels. And again, because potassium changes can very quickly lead to arrhythmias, to heart problems, to neuron problems. So our plasma levels, our potassium levels in the extracellular fluid in the plasma and interstitial needs to be very low. It needs to be somewhere between 2.5 millimoles to 6.5 millimoles. If it's high, that means there's more potassium outside the cells than there should be. You might see hyperkalemia. And hyperkalemia could occur because you're doing too good of a job bringing potassium in at the gut. You're maybe having cells, too many cells, dying or releasing potassium. And that can happen because insulin's not being effective or being made efficiently or effectively being responding to. Again, anytime a cell explodes, anytime a cell dies, potassium's released. And one of the big things for the skin, for pain receptors, is if potassium is in the extracellular fluid, that interacting with free nerve endings triggers pain, triggers itch, triggers discomfort, because that's a signal that potassium is not supposed to be there and a cell must have died or exploded or been injured. Okay. You reduce it in the excretion because you're acidotic, and because you're acidotic, the kidneys are working to get rid of the hydrogen ions, and so in doing that, you're not then able to secrete as much potassium. Right? If you don't have aldosterone being made, like in Addison's disease, you might have hyperkalemia. Right? And then there's some other reasons. Now, the big thing about high potassium is now the gradient for potassium wanting to leave the cell is not as robust, so less potassium leaks out. And that translates at the heart to changes where the cells are going to, as pacemakers in particular, not maybe repolarize or hyperpolarize, and they are going to be more likely to hit threshold and faster to hit threshold. And so that can lead to mismatches and cells getting out of sync and arrhythmias occurring. Okay? And so again, we try very hard to try not to let potassium levels get too high, because then that can translate to arrhythmias, hearts skipping beats, the ventricles not being tied to the atrias beating, and then that could mess up with delivery of cardiac output and blood pressure and oxygen to key places like the brain. Okay. On the flip side, hypokalemia is you're either not taking it in and you're losing greater than you're taking it in. It could be because the renal system is damaged in some way and you're not able to retain it. It could be because there's too much insulin and too much influx and retention of potassium in the cells and some other factors. And so in this kind of situation, now you're maybe hyperpolarizing your cells. So your muscle cells can't get to threshold and can't contract. So paralysis occurs because, one, you can't get muscle contractions to occur in an appropriate manner, right? And then on the ECG, again, problems between the matching of the pacemaker cells to the ventricles and the tying of the ventricles and the pacemaker cells and contractions diastole and systole, and again, arrhythmias and problems occurring at the heart. Okay. All right, the next big electrolyte we need to talk about is calcium. Calcium is mostly inside cells, but calcium does a lot of things. In neurons, it's important at synapses of getting a neurotransmitter released. So if you don't have calcium and sufficient amounts of calcium outside the cell moving into the cell and then inside the cell triggering docking and vesicle release, you might not have neurons able to talk to muscle cells, talk to glands, or talk to other neurons. You might not have clotting processes working effectively if calcium levels are not sufficient in the extracellular fluid, specifically in the plasma. And then you might not have sufficient amounts of calcium releasing troponin, tropomyosin, blocking of actin sites in skeletal muscles, so you might not get as strong of muscle contractions for the skeletal muscle. So a lot of things can go wrong. And then for the G proteins that utilize calcium and IP3 and certain second messengers, you might not get those amplified signals, and so you might be less responsive to those hormones that use calcium as a second messenger should intracellular calcium levels be not sufficient. All right. So again, you regulate calcium levels in your blood and your extracellular fluid through hormones, parathyroid and calcitonin. And calcitonin has an L, so that's how you lose blood calcium. So it's one of the ways you try to bring down blood calcium, by losing it, by making the gut not take it up, by making it go into bone, by making the kidneys put it in the filtrate and secrete it. On the flip side, parathyroid hormone helps you raise blood calcium. So it's got the R to raise calcium. And so parathyroid works to make you release calcium from your bones, release or retain calcium from the kidneys, and bring in more calcium from your diet. Okay. Chloride ions are normally going to match whatever sodium's doing. The only difference is chloride is negative, so chloride electrically doesn't want to go into the cell as robustly as your sodium ions. Now remember, in red blood cells, chloride is how we shift with chloride levels taking the place of a bicarb. So chloride will be utilized to help us in some ways maintain bicarbonate concentrations between inside red blood cells and outside in the plasma levels. Okay. All right, and again, you usually see chloride following sodium. So chloride, we know, is important because if you don't have a chloride channel and the ability to move chloride, you can end up with a whole condition known as cystic fibrosis. So again, we monitor our major cations and anions, and we keep the balance of these solutes to, drive membrane potentials and change membrane potentials. But in doing so, we then actively pump them back to stable levels and to resting levels, and in doing so, that helps us somewhat maintain water balance. And many hormones help us maintain their levels, so therefore we control the electrical properties across cells, but also help control their contribution to solute levels and water balance. Okay. The last piece of this is acid-base. All right, and there's some terminology and some chemistry we have to go through. All right. pH changes because hydrogen ions accumulate or hydrogen ions decrease in solution. Okay, and so high acidity means the pH is very low, meaning the hydrogen ion concentrations are really high. And then conversely, bases are going to be considered low concentration of hydrogen ions, really high pH numbers. Okay, now acids are going to be any kind of molecule that when you put it in a water solution are going to donate a hydrogen ion, meaning the molecule, the original molecule, disassociates into a hydrogen ion and a negative ion, but they stay in ionic form. Okay? So hydrochloric acid is a very strong acid. It is hydrogen and chloride ions ionically bonded to each other. When you put them in water solutions, they disassociate into the hydrogen ion and the chloride ion. And they are considered a strong acid because in any given second, most of the hydrochloric acid is disassociated in water into its chloride ion and its hydrogen ion. Okay? There are other acids out there, right? Carbonic acid. Carbonic acid is water and carbon dioxide forming this molecule, and then in water, it dissociates into a hydrogen ion and a bicarb ion. It's considered a strong, a weak acid because at any given second, some of the hydrogen ions are reforming with the bicarb to carbonic acid and then dissociating into carbon dioxide and water molecules. All right, and so even though there's potentially carbonic acid in the solution, it's in flux at every second to dissociating to hydrogen ions bicarb, reassociating to carbonic acid, and then dissociating into its carbon dioxide and water levels. So it's a very easily reversible reaction, but depending upon the concentration and the state of the reaction, it's either flowing towards making a lot of hydrogen ions and bicarb molecules or flowing towards carbon dioxide and water. Lactic acid is another molecule. Lactic acid, again, comes from pyruvate accepting that hydrogen ion, and it recalibrates itself from NADH to NAD and a hydrogen ion, and pyruvate accepting that hydrogen ion becomes lactate acid, and that is basically a negative molecule. That is what is left of pyruvate once it binds that hydrogen and then dissociates into the lactate and the hydrogen ion. Okay? So when you look at this picture, what I'm trying to show you is any molecule that has a hydrogen ion that could, in water, donate that hydrogen ion is considered an acid. Weak acids, some of the molecules stay ionically bound, and so the hydrogen ion stays somewhat bound to the negative piece of the molecule. Strong acids, almost all of the molecules dissociate into the negative part and the positive part. Okay? Bases are going to be any molecule that binds the negative or the hydrogen proton. And strong bases are going to be bases that, when in solution, tend to stay in bound form with the hydrogen ion bound to it, versus weak bases are going to be less likely to have all of the protons, all of the hydrogen ions sufficiently in bound form. Okay? All right, so again, we tend to look at ion balance, specifically hydrogen balance, as what are the acids that are contributing protons and the hydrogen ions to the solution? What are the bases we have that could be potentially buffering and compensating and taking some of those hydrogen ions and putting them back in a bound molecular form? All right, and then what is hydrogen able to bind to and form salts? Now, our pH is very narrowly controlled to what is the concentration of hydrogen ions that lead to a pH of 7.35 to 7.45. All right, and that is blood plasma ion concentration. The inside of the cell can be a little bit more fluctuating, but the outside of the cell, and specifically the plasma, needs to stay between 7.35 and 7.45. Anything lower than 7.35 is considered an acidotic state. Anything over 7.45 is considered an alkalotic or a basic state. Okay? Now, to keep the hydrogen ion levels within this range, we have a lot of buffers. Buffers are strong bases or weak bases that, when presented with hydrogen ions in solution, can somewhat form ionic bonds, form molecules that then decrease or prevent the accumulation that causes large shifts in hydrogen ion concentration. Right? So some of the buffers in our blood are actually bicarbonate, because bicarbonate can combine with the hydrogen ion to form carbonic acid, and that's a weak acid, and so in this molecule, some of it is in a bound form. There are a lot of proteins and a lot of amino acids out there that actually have negative pieces or parts of it, and those negative pieces and parts, you know, whether it's a hydroxy group or a phosphate group or whatever, can bind a hydrogen ion, forming a protein that then is no longer negatively or has a negative component. And then hemoglobin, again, has the ability to have proteins and amino acids as part of it, and so it's going to potentially, like other proteins inside the cell, somewhat have a negative piece. But that negative piece could bind to a hydrogen and again form the new molecule of hemoglobin that's no longer negatively charged. And those are a lot of our buffers in our bloodstream. So our plasma proteins, our hemoglobin, and our carbonic acid helping to facilitate making and breaking carbonic acid into either the hydrogen bicarb part or the carbon dioxide water part are going to be some of our big buffers in our blood. Okay. The one thing to note is these proteins can be plasma proteins, so they're part of the extracellular fluid, or they could also be some intracellular proteins inside red blood cells. All of the hemoglobin here is inside red blood cells. So it's a buffer for blood, a buffer for an extracellular fluid, but it's actually inside cells, part of the red blood cell intracellular fluid. Now, all of our interstitial fluids have some carbonic anhydrase and so have the ability to somewhat buffer hydrogen ions by making and then transversing bicarbonate and hydrocarbon into carbonic acid. Okay? And inside the cells, cells have a lot of proteins. They have a lot of proteins and amino acids that can be buffers, and then they have phosphates. And remember, they use phosphates to bind and make the backbone of DNA and RNA, and so they have a plethora of phosphates, as we learned in our ICF balance earlier picture. Okay. So again, any condition that leads us to accumulating a lot of hydrogen ions and therefore our blood pH becoming less than 7.35 is going to make us into an acidotic state. And anything that brings us above 7.45 is going to be an alkalotic state. Right? So again, our body, where do we get these acids that potentially drive us to become acidotic? Well, we have some fixed acids, and these are acids that do not leave solution. They are going to be produced in the liver. They are produced as part of our body's metabolic processes. They can be potentially eliminated at the kidneys, but they don't always have to be eliminated at the kidneys. All right? Some of our fixed acids include sulfuric acid and phosphoric acid. And then other ones are amino acids, phospholipids, and nucleic acids. And again, we want to keep amino acids, we want to keep nucleic acids because these are our building blocks of proteins, these are our building blocks for RNA and DNA. So these are acids that we know are going to have inside our body, and we know that while we can remove some of them at the kidneys, we really don't, and they don't leave the solutions of our intracellular or extracellular fluid. The next type of acid we have are our organic acids. And these are usually the acids like lactic acid, ketoacidosis, that are made because of trying to make energy for our cells. Okay? And they can be metabolized and broken down into other components and parts, and so they don't usually accumulate, but if we end up with situations where the ATP is not sufficient, they could accumulate, and when they do, they could build up very rapidly. The third type of acid are our volatile acids. These are going to be the acids that can change conditions and shape very easily, and these are the ones that we use to help us at the kidneys and at the respiratory tract and the GI tract potentially rid ourselves of acids and secrete acids into the airways, into the filtrate, or into the lumen of our digestive tract. All right? And so this is the carbonic acid. Carbonic acid is a volatile acid because it can leave solution and enter the atmosphere, but it can also be something that is dissolved in fluid. Okay? All right, so carbon dioxide is considered an acid because when carbon dioxide is dissolved in water, in the presence of carbonic anhydrase, large amounts of carbon dioxide gases are going to, once dissolved, combine with water to form carbonic acid. Carbonic acid, as a weak acid, will dissociate into a hydrogen ion, and some of those hydrogen ions will be donated to the solution and a bicarbonate ion. Okay. So we manipulate, we know we're going to make carbon dioxide in our cells, and while it's volatile, if we can get it to the respiratory tract, that carbon dioxide will leave as a gas. Until we get it there, it's a volatile acid and it's being carried as carbonic acid and as hydrogen ions and bicarb in our fluids of our body. We know we're going to make organic acids, we're going to metabolize, we're going to potentially, if we're rushed and needing more ATP than we have oxygen available, we will make more lactic acid or ketoacidosis or keto acids, and those will accumulate and potentially alter ion and pH levels inside, outside the cell. And then we know we have fixed acids, that we have amino acids that we need to make proteins, and we need nucleic acids to make RNA and DNA. And then we need phospholipids so that way we can make our membranes of our organelles in our cells. And those we're not going to try to lose, and we'll lose a little bit here and there, but we're going to try to retain. So we have to have bases to match the acids we know we're going to have that we're never going to leave or not likely to leave, and to match the acids that we accumulate through different processes. Okay? And our goal is to have enough bases and enough buffers so we don't see big shifts in pH, and we can kind of mask and handle and bind the excess hydrogen ions until we get to a place where we can secrete them, infiltrate, secrete them into the GI tract, or allow the volatile acid carbon dioxide to leave through the respiratory tract. Okay. So again, hydrogen ions are gained in a variety of mechanisms. They can be gained through acidic foods, through gaining proteins, through gaining amino acids, through gaining phospholipids, through gaining nucleic acids in our diet. And they are eliminated, and they are gained again through making organic waste, making more carbon dioxide gases through metabolic activities. And they are eliminated by secretion at the kidneys. They are eliminated by the release of carbon dioxide, the volatile acid, then carbonic acid releases carbon dioxide at the lungs. And they are released and neutralized with buffers and with other binding mechanisms to try to prevent the hydrogen ion accumulation to cause acidity or basic circumstances that could damage cells, damage proteins, damage functions. Okay? Until we can get them to the kidneys and in the filtrate, until we can get them to the lungs and carbon dioxide leaves, we have a situation where we need some type of way to neutralize so we don't see hydrogen ions accumulate swiftly and in large amounts. And that's where buffers come in. Buffers are in some ways any compound that can help us stabilize pH by binding and therefore removing a hydrogen ion from solution. So while weak acids typically donate hydrogen ions, the components of the weak acid, like bicarbonate, could potentially bind a hydrogen ion and temporarily buffer it. So some weak acids, the parts of the weak acid, again, being the negative part, can help us take away hydrogen ions. So we'll find some of the negative parts of weak acids in our buffer system. Other ways to buffer are using weak bases, which, again, are in circulation as negative components like proteins, like amino acids, like those phosphates, that then can very quickly help us bind excess hydrogens, and in doing so, take the hydrogen concentration that's free-floating in the fluids of our extracellular fluid or intracellular fluid and decrease it because they're now in a bound form as a part of a different molecule. Right? When we look at our buffer systems, they are composed, again, of some weak acids and some anions that can bind hydrogen ions, forming, again, neutralized molecules or salts. Right? Our buffer systems, we tend to have three big buffer systems. Okay? We have buffer systems located inside the cells and buffer systems located outside the cell in the extracellular fluid. Right? Because phosphate ions are negatively charged molecules and tend to be hoarded in the cell, the phosphate buffer system is strictly found inside the cells. And it's typically going to help us buffer hydrogen ions that are made through metabolic purposes, through the organic waste, through the fixed acids that we have inside the cell. Okay? The extracellular buffer that's entirely in the extracellular system is the carbonic acid bicarbonate buffer system. So this is that carbonic anhydrase that's found in the extracellular fluid and helps to convert the carbon dioxide gases dissolved in water to bind with water, form carbonic acid, and then dissociate the hydrogen and bicarbonate ions. We tend to then add to the extracellular fluid excess and more bicarbonate ions so we can enhance and facilitate more hydrogen ions to be able to, in a given second, in a given circumstance, combine with bicarb to form carbonic acid. And in an acid-bound form, the hydrogen ion concentration that's free-floating in the water of our extracellular plasma is less than what it could be. Okay? The third system is actually found in both. We find proteins circulating in plasma, we find proteins circulating in interstitial fluid, and we find amino acids that are the building blocks of proteins in plasma and interstitial fluid and inside cells. So any place we have a protein, any place we have an amino acid, we potentially have some of these proteins and amino acids have R groups, have portions of it where they could potentially bind a hydrogen ion, and instead of having a negative orientation to that molecule, could then become neutral. Right? And so the plasma proteins, so our albumin, so our fibrinogen, so our immunoglobulins, so our transport proteins, our antibodies, many of them are going to have these R groups that are negative in generally charged, and so potentially have the ability to bind hydrogens when they're in excess, and in a given second, because they're binding the hydrogen, the free-floating hydrogen ion concentration is not as robust as it would be without these ions binding to these proteins or these amino acids. Okay? And then inside the cells, there are proteins. All right, and so inside cells, there are proteins that can also enhance and bind, and specifically to red blood cells, hemoglobin is a specific protein that can be found to bind hydrogen ions when in excess, and we saw that, and then assist with maintaining blood pH levels. Okay, so again, how does it work? All right, many of our proteins, this is where we start. Many of our proteins have that amine group, which we talked about is a problem because that when we want to make the protein into something that could be a fuel, we have to get rid of. But the other part of the protein is this carboxyl group. And that carboxyl group, one of the parts of it is this OH. And that OH is considered a weak base. Sometimes that OH is donating a hydrogen to the solution and therefore helping keep pH and the free-floating hydrogen ion levels at a certain level. In other situations, when the hydrogen levels start to increase, that is going to increase the odds that some of those hydrogen ions are going to bind back to this oxygen molecule and thus, in bound form, negate some of the hydrogen availability. And in addition, the nitrogen can accept additional hydrogen ions, and in doing so, help again negate some of the buildup of hydrogen ions in the free-floating form of the fluid. Some of our R groups are going to have, again, some nitrogen pieces, some carboxyl pieces, or some other things like sulfur or phosphates. So some of our amino acids can accept more hydrogens not only from the amine and the carboxyl group, but from the R group, and in the reverse can donate hydrogens from more carboxyl groups being present potentially in their R group. Okay. All right, the protein buffer systems, again, are going to be very similar. Proteins are composed of amino acids. So if amino acids have amines and carboxyl groups, then proteins have amine and carboxyl groups and can potentially take on, like amino acids, more hydrogens and by those amine or carboxyl groups or other groups that are in the R group. Okay, and you find proteins in the blood, specifically as plasma proteins, and you find proteins inside red blood cells in the form of hemoglobin. But you also find proteins in intracellular fluids because proteins are found inside cells. And so this protein buffer system is in both places, both helping us inside the cells and helping us outside the cells. Okay. All right, the hemoglobin buffer system, where is hemoglobin found? In red blood cells. Where are red blood cells found? Only in the plasma. So this type of protein buffer system is actually specific for protein buffer systems only in the plasma. So it is one of those special protein buffer systems that is going to, while being intracellular protein, going to have a very pronounced and robust effect on extracellular plasma ion, hydrogen ion, pH levels. Okay? And it works by carbon dioxide as a gas can flow easily across the membrane into the red blood cell. And when the carbon dioxide flows in, there's water in the cytosol of the red blood cell. And some of that carbon dioxide in water, because there's a protein carbonic anhydrase, is going to become carbonic acid. If there's a lot of carbon dioxide, that means the drive will be more carbon dioxide and water combined to form carbonic acid. As there's more carbonic acid becomes hydrogen ions and bicarb. All right. As we want to keep this going to help the cells get rid of more carbon dioxide, we are going to take some of those hydrogen ions and bind it with hemoglobin. By doing that, there's less hydrogen bicarb to combine back into bicarbonate or carbonic acid. So that facilitates movement at tissues for more carbon dioxide to be taken out of the cells. And more hydrogen ions bound as hemoglobin. More of the bicarb enters into the plasma so it can buffer in the plasma. More carbonic acid is made from the combination of carbon and hydrogen. When you get to the lungs, the reverse happens. We are losing carbon dioxide into the air. So this reaction becomes the carbonic acid levels decrease as carbon dioxide levels are leaving. So more hydrogen then is released to form more bicarb and hydrogen into carbonic acid, and that facilitates more carbon dioxide being offloaded at the lungs. Okay. Again, doing all of this to keep hydrogen in and to allow bicarb to go and be a buffer in the plasma, for a negative to leave the cell, a carbon has to come in, and the chloride shift occurs. Okay? So the hemoglobin buffer system, again, it's an intracellular system. Hemoglobin is found in red blood cells. Red blood cells are only found in the plasma of our system. So this is the only intracellular protein system that has a very immediate and pronounced effect on plasma pH levels, and plasma is part of the extracellular fluid. Okay. Now, the third system is specific to the extracellular fluid, to plasma levels, and again, it goes back to carbonic acid, bicarbonate levels, hydrogen levels, and which side of the equation? The carbon dioxide dissolved in water to form carbonic acid, dissociate into hydrogen and bicarb, or there's more hydrogen and bicarb, so it forms carbonic acid, which can dissociate into carbon dioxide and water. Okay? So this buffer system, some things to note. It cannot protect the ECF from changes in pH that result from elevated or depressed levels of CO2. It functions only if your respiratory system works. Okay, because if your respiratory system is working, you have an ability for carbon dioxide levels to leave or leave. Okay, and this buffer of acids is limited to how many carbonic ions you have. So again, somewhat the kidneys have to work to retain bicarbonate ions to help facilitate this system to work. Okay, so again, let's talk about it. One of the limitations is you have to have a functioning respiratory system. So you have to be breathing for this system to work. The second is you have to have bicarbonate ions. So where do we get bicarbonate ions? One, we retain them in the kidneys. So normally we have retained bicarbonate ions in the kidneys. Now for a given second, for a given period of time, we might not need that nice, robust bicarbonate plethora in our plasma. And so what we see is the bicarb, because it's a negatively charged ion, could, with the high amounts of sodium ions, which is a positively charged ion, in interstitial fluid and plasma levels combine to form a salt. And that salt is sodium bicarbonate. And when it's bound this way, there's not then a lot of free-floating bicarbonate. Not a lot of free-floating bicarbonate allows, depending upon the situation, the equation to move towards carbon dioxide, or carbon dioxide and water levels to move towards hydrogen and bicarb, and allow us to sufficiently then carry carbon dioxide levels from the tissues to the lungs, and then again maintain pH balance. Okay. All right. Phosphate buffers, again, are located inside our cells. Again, phosphate is a weak acid. It normally, when in water, is at any given second a phosphate and a hydrogen ion, or a phosphate hydrogen ion non-charged molecule. Okay? So at any given second, the equation is moving from positive to non-charged, all right? Positive to non-charged, or positive, negative. Positive, 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 negative. Okay. And it's important in our intracellular fluid because we have a lot of phosphate ions. Phosphate being the backbone of DNA and RNA, and important that it binds and becomes part of ADP to ATP, AMP to ADP, GTP, GMP, UTP, UMP, and all those nucleic acids that can form phosphate. It's a temporary solution because while it's buffering the hydrogen inside the cell, neither molecule is going anywhere. So the hydrogen is not leaving and the phosphate is not leaving. So ultimately, you need to potentially have the proteins, the carbonic acid, and the ECF set up a situation where it can then pull those hydrogens into it because it's removing hydrogens in the lungs and in the urinary tract. So this system is limited and it's only a temporary fix. Okay. So for homeostasis to be balanced, you have to capture hydrogen ions temporarily at any given point in time until you can remove them, and then you need to be able to remove them from the body fluids. You remove them by removing carbon dioxide at the lungs, or removing them through the kidneys through secretion in the urine. Okay. Conversely, to maintain or preserve the buffers, we need to maintain the buffers, again, by not losing too much carbon dioxide, so we don't then lose potentially some of the acid load and some of the levels of buffers. And then we need to basically retain them or lose them appropriately in the kidneys through renal mechanisms. Okay. Now, anytime we have a situation where we're potentially maintaining too much buffer or maintaining too much acid, the other side of the system usually tries to compensate. So let's talk about breathing. If we are not getting rid of sufficient amounts of carbon dioxide, we would be potentially hypoventilating. So we're not getting rid of a sufficient amount of carbon dioxide levels, and we would then be retaining too much acid. Well, in order to compensate for that, our then bodies would try to get rid of more acid at the kidneys and potentially increase our breathing rate. And by increasing our breathing rate, we would try to then turn from hypoventilating to the correct amount of ventilation and removing enough acid through the CO2 loss, and then potentially even removing excess acid at the kidneys. On the flip side, if we're hyperventilating and moving acid too quickly from the lungs because we are letting too much carbon dioxide leave too fast, again, we have systems set up to try to slow us down by detecting that change in pH level at the carotids and the central chemoreceptors. And then again, we might do a better job of maybe ridding some of the base that we accumulate or typically retain in the urinary system. Okay. So again, acid-base, it's a match of what are we doing at the respiratory tract, and are we doing an okay job, and can we change the respiratory system to better release or retain carbon dioxide, versus what are we doing at the urinary tract? How are we doing with retaining bases, releasing hydrogen ions, and then manipulating that? And so any point in time, if the lungs are not able to compensate by themselves by manipulating respiratory rate, the kidneys could try to compensate by doing a better job or less better job of retaining, making acid-base balance, and vice versa. Okay? And again, we do that at the kidneys by maintaining or releasing buffers in our urine. All right, so let's get into it. What are our types of acidosis? Okay? And what are the kidneys' response when we have an acidotic event? All right, so acidosis is any situation whether we are not sufficiently releasing carbon dioxide at the lungs or making acids faster than we can get rid of them at the kidneys, so we have a buildup of hydrogen ions. Anytime we have a buildup in hydrogen ions, that's going to be detected through the central chemoreceptors and through the respiratory mechanisms, and we probably will see the respiratory rate increase. And the respiratory rate increasing is going to try to get rid of more carbon dioxide to help us get rid of acid. The kidneys, on the other hand, are going to do a better job of trying to secrete more acid into the filtrate at the PCT, the DCT, and everywhere. And in compensating for, again, high hydrogen levels in the body, they're going to also do a better job of tying sodium absorption and therefore bicarbonate reabsorption to try to then have more buffers in the body. Okay. The kidneys can also try to remove more carbon dioxide dissolved in the urine and do more reabsorption of sodium and bicarbonate. Okay. And so between increased respiratory system, getting more carbon dioxide out, getting more secretion of hydrogen into the filtrate, and retaining sodium and bicarb, the kidneys and the lungs in an acidotic state would try to then fix with that type of compensation. On the flip side, if we start to have hyperventilation, and maybe we're getting rid of carbon dioxide too quickly, and we have too many bases, maybe we had some diarrhea and we've lost we've vomited and we've lost too much acid and we're having issues with too many bases, the kidneys are going to help us in this alkalotic state by retaining actually our retaining our hydrogen ions, and in retaining hydrogen ions, we're going to end up losing more sodium and bicarbonate into the filtrate. Okay? And then maybe slowing our breathing rate down so we don't then lose our hydrogen carbonic acid as quickly, so we would expel less carbon dioxide. Okay? All right. Again, what are some of the acid-base disturbances? Anything that increases hydrogen ions or buffers in the blood could end up being an acid-base disturbance. Acid-base disturbance can really quickly turn into heart failure, hypertension, lots of bad things happening both neurologically and muscle-wise. Okay? Normally, acid-base disturbances happen in the short term. It's an acute phase, and we do short-term compensating effects. If they stay around and the condition is going to be more permanent, we will then see compensation occur more robustly by more robust mechanisms, both with changes permanently to respiratory rate and permanently to secretion and reabsorption of sodium and potassium and hydrogens and bicarbonate at the kidneys. Okay. All right, respiratory acid-base disorders occur because of whatever's happening at the respiratory system. We're not sufficiently getting rid of the carbon dioxide with the air, or we're not getting enough carbon dioxide out with the air. That can occur because of whatever's going on. There's a problem with the airflow, the delivery, the amount of lung, air, surface area, and interchange. Okay? Those changes will very quickly be seen in the extracellular fluid and be seen with problems with the carbonic acid as well as the hemoglobin buffer system. Okay. Metabolic disorders are occurring either at the cellular or the kidney level. So they result from cells having problems making more organic and fixed acids, or the kidneys not sufficiently removing acids like they should into urine. And the concentration, and we'll see that, affect the intracellular content if it's happening at the cell level, or the kidneys not working and removing acids will cause the extracellular changes. Okay. So in response to acidosis, again, we're going to work through respiratory and kidney mechanisms to get rid of hydrogen ions. So what we will see is if we have an acidotic situation, we are going to, at the lungs, try to increase respiratory rate and increase the removal of carbon dioxide. On the kidney side, we're going to do a better job of retaining bicarbonate ions and maybe sodium with it, making more bicarbonate. For our bicarbonate reserve we have, we're going to release more of that bicarbonate to be available to bind hydrogen ions. And then we're going to use other systems that can bind hydrogen, like the phosphate system and other proteins to bind temporarily hydrogen ions. And then we're going to work really hard in the kidneys to do a better job of secreting more hydrogens into the filtrate and retaining more bicarbonate and sodium with it. Okay. And everything that we just said is reversed when we look at the alkalotic situation. Okay. What is the most common way we can end up with a problem acidotically is we can end up with respiratory acidosis. Right? So when we have a system where we're hypoventilating, could we be hypoventilating because we're on a ventilator and the tidal volume and the respiratory rate is not sufficient to meet our demands? Yes. Okay, so something like that could end up being respiratory acidosis. So we are generating more acid than we can eliminate CO2 fast enough. Okay, so we're hypoventilating. And we will try to acutely increase the ventilation rate. But if you're on a ventilator and you're not conscious and you're not able to then compensate that way, what we'll see is respiratory acidosis has to be metabolically compensated, meaning the kidneys have to try to compensate by then working better to get rid of acid. And if that person on that ventilator is in kidney failure, that is a problem. Okay. Respiratory alkalosis is a condition where because of the respiratory system we might not be able to we might be getting rid of more carbon dioxide faster than we're making it or adding acid to the system. Okay, and this is when someone hyperventilates. Okay, so they are hyperventilating, moving too much carbon dioxide too fast. Now let's focus on the metabolic disturbances. Metabolic acidosis is also very common in our system. And it's common because for short-term purposes, when you exercise, if you are exercising at anaerobic threshold or exercising at some really big high-intensity involvement volume and intensity, you could become temporarily metabolically acidotic while doing that event. As you burn more glucose and make more lactic acid, you could become metabolic acidosis. So we see this sometimes with post-Ironmans, post-races, post-marathons, that people are slightly metabolically acidotic. And for a short period of time, we might see them stay with an elevated breathing rate to try to get rid of some of the acid by respiratory compensation. And we might see they have really concentrated urine that's really acidotic following that event as well. Another place metabolic acidosis can occur is when people who are diabetic are not monitoring and keeping their insulin and glucose levels efficiently, and so they go into that starvation mode and start making molecules that shouldn't be made or normally made into energy molecules and start generating that acetone and that carbonic acid or keto acids. Okay. Severe diarrhea can lead to metabolic acidosis, again, because the GI tract below the stomach is all about bases, and so when you lose all those bases and your body is trying to put more bases into the GI tract in the small intestines, you're then excessively losing your bases that are now not available to be in your plasma. Okay? And then impaired kidney function, where you can't get rid of your acids when you are a normal person, could also lead to metabolic acidosis. Okay? And again, metabolic alkalosis is the reverse. You're getting rid of more acid than you are base, or you're not efficiently able to get rid of base. Okay? And so you have elevated bicarbonate. And you see this with people who throw up a lot. Okay, so if you were to throw up a lot, now you're losing acid from the stomach faster than you should, and so you're having to constantly make more hydrogen chloric acid to put into the stomach, and so you might end up with more base in your system than you meant to have initially. Okay, and that could lead to, again, metabolic alkalosis. All right. Again, detection of acidosis and alkalosis is done by taking a blood sample and just checking it. What is the pH of the blood? If it's below 7.45, above 7.45, you would maybe be a little alkalotic. When you're below 7.35, you might be a little acidotic. And with athletes, part of what they do when they train, they want to train sometimes right around that anaerobic threshold, that point where their oxygen is maximally meeting potentially the ATP demand, and all of their mitochondria are working at max capacity, and all of their energy is being consumed through aerobic mechanisms. And when they start becoming acidotic, so little blood draws in the middle of the activity are starting to let them, and researchers and people know when maybe they're crossing over into that state where they're no longer meeting oxygen demand and they're accumulating acidosis and acidotic and lactic acid. Okay. Once you check usually the blood pH, unless in a runner situation you know what's being caused. But if you're just a Joe Blow off the street, you have to sometimes do a little investigation. Why are they acidotic? Is it because of a respiratory or a metabolic issue? And so if you look at, okay, their blood draw tells me they're in acidosis. And then I check their respiratory rate, and I check the amount of carbon dioxide coming out of their system. If the respiratory rate is elevated and they have a lot of carbon dioxide coming out, I might be seeing that they are respiratory acidosis. If they're normal with their PCO2 and their breathing rate, it might be they are in metabolic acidosis. And then you go and continue down this little pathway. And you're going to do this more in nursing. I just want to slowly introduce it here, is that when you look at patients in ICU, you are going to potentially have patients in ICU on ventilators or sedated or in comas or in a situation where you have to monitor their urine output, you have to monitor their airway, you have to monitor if you are efficiently seeing what's happening for respiratory and urinary systems. Are they working sufficiently, and are we ventilating them, and are the kidneys functioning to maintain the pH balance? And if they have some underlying respiratory disease or lung disease or kidney disease, you might have to pay more attention to, are we monitoring and handling and keeping this patient in pH balance? And doing that might mean you have to do some compensation. Okay, and that's really what the last of these slides are. So in summary, all right, how does a person become alkalotic? They can become alkalotic because they hyperventilate and lose too much CO2. They can become alkalotic because they get anxious and they hyperventilate. They can become alkalotic because they go to high altitudes and hyperventilate and air hunger happening. They can become alkalotic because they're pregnant and they can't breathe as deeply because of the baby, so they start to breathe at a higher respiratory rate. They can become alkalotic because of lung disease and pulmonary embolisms. Okay, and not being able to get carbon dioxide from the bloodstream into the airways. Okay, how can we get people, again, to become acidotic? Well, there's a part of that can happen because of respiratory mechanisms. All right, hypoventilating, airway obstruction, chest trauma, overdosing in drugs that depress the breathing rate of our bodies while we're sleeping. Okay, and then how can we get alkalotic by metabolic means? Again, you throw up too much. You take too many antacids, all right, or take too many potassium-wasting diuretics that also lead to loss of too much, too quickly, hydrogen ions, right? Or how can we become acidotic through metabolic mechanisms? We have diabetes and we're not controlling it. We have renal failure. We have diarrhea that hits us too fast, too quickly. Okay, and again, in babies, big deal, because babies have small volume to weight ratio, and so excessive diarrhea or excessive vomiting is a big deal. I have a friend that was just talking about, she fosters a baby kitten, and the baby kitten for like 24 hours was constantly throwing up and diarrhea, and she was worried the kitten was going to die, and didn't want to withhold food because it was so small and because it was anemic, and so they basically put the kitten in a sedated state and with IVs until the little, I guess, medication of heartworm or whatever ran its course. Okay, so again, babies, if you work on the NICU and you see babies that are in distress, respiratory distress, they're going to be monitoring acid-base problems that could be associated with that. And that is the chapter. Yay! All right, so this is your homework. This was your stuff you needed to listen to over the Thanksgiving break. We'll get started on reproduction when we get back. We've already kind of started on reproduction in lab this week and rat dissections for lab, and then the last week of school. Last week of labs will be lab exams, and then final exam will be during finals week, but it's over chapter 26, 27, and 28. All right, have a good Thanksgiving, you guys.